key of the business today. Function is finished today. RT and J.
What is going on, everybody? It's your boy Average Leader here with another video. Today we're tackling top K frequent elements, number 347 on Leetcode. This question is commonly asked by Facebook, Capital One, Amazon, Bloomberg, Oracle, Apple, and a few other companies here. I actually got this question from my Bloomberg phone screening interview, and unfortunately that didn't go my way. I did not move on after that one, and it's mainly because I messed up on my runtimes, so that's super important. But we'll go through those, towards the end of this video. But before we start, if you guys can go ahead and hit that subscribe and like button, that would mean the world to me. It really helps my channel out a ton by giving it more exposure to people that don't know me. And also, if you guys can take one thing from this video, go to this timestamp. Okay, it's a big key for solving many problems like this one. And with that all out of the way, here we go. So, given a non-empty array of integers, return the k most frequent elements. Okay, cool. Let me see some of these examples. So when our input is 1, 1, 1, 2, 2, 3, so we see that there's 3 1s, 2 2s, and 1 3. So and it's asking for the 2 most frequent elements. So we see that 1 and 2 have the most count, so that's why we output that. And we're just given an array of 1, and we're asked for the first most, the first most frequent element. We just output that 1. Okay, so I think for this one, let's just go to the iPad and just do a few examples, try to figure out what we're actually doing in this problem. Okay, so working with the example that was given to us in the problem, like I said, we are given 3 1s here, and then 2 2s, and 1 3. And because of the 3 1s and the 2 2s, these have, the 1s have the highest frequency of 3, 2s have the second highest frequency of 2. We know that these 1 and 2 ultimately will give us the output for the top 2 most frequent elements, right? So what did we exactly do there? Well, let's just see really quick. We went ahead and scanned our input array, and we just found the counts of each of our distinct elements, each of our unique elements. So for 1, we noticed that there were 3 of them, right? There are 3 1s. And for 2, we noticed that there were 2 of them. And for 3s, we noticed that there was 1 of them. So in order to get the k most frequent, the top 2 most frequent, how can we tell what's the most frequent element using these 3 things, right? Well, we see that 1 has the highest frequency and 2 has the second highest frequency. So this really just comes down to ordering our frequencies somehow. So how can we order our frequencies? Something that I'll typically do in an interview setting is think about all the data structures that I could use, or maybe just think about all the data structures and then just narrow down what we could actually use. So off the bat, let's just think about this. So we have array list, linked list, we have queue, we have stack, we have heap, we have binary tree, BST, binary tree of sorts. What do we have? A deck, and hash map, hash set. Okay, so we'll just use these for now. But now let's just think about this. What could give us some sort of ordering? Well, we have an array list, and that one has like some sort of, we have like collections that sort that we can use there, so we'll keep that one in mind. Linked list, I'm sure it also has collections that sort, but it's just the same as array list. Queue, stack, I don't really see being useful here, so I'm just going to take those out. Just because queue and stack are like ordering in the FIFO and LIFO, first in, first out, and last in, first out. So I really don't think we need that here. Heap, this one's interesting because this one we'll always have access to the minimum element at the top or the maximum element at the top. And if we have the maximum element at the top, then we'll have the second max element right after it. We'll have the third max element right after it if we have a max heap. So that's interesting. We'll keep that in mind. BST maybe doesn't make a lot of sense. Dec doesn't make a lot of sense. Hash map, hash set doesn't make a lot of sense here in our case. So using the ones that we have left, right, heap, array list, and linked list, I really like how the heap keeps, like if we have a max heap, we can keep the max elements or the most frequent elements at the top. So most freak at the top, and then the second most, and the third most, and the fourth most, and so on and so forth, which in a way is kind of what we're doing here, right? Like if we were to somehow manipulate the heap so that we can put one, so here, I'll put this. If we can manipulate it somehow so we can put one at the top, because this one has 3 occurrences, and then 2 after that, because this one has 2 occurrences, and then 3 after that, since this one has 1 occurrence, and just popped out k elements, because we're looking for the k frequent elements. If we just, so in this case, k is 2, so if we just pop this thing twice, we'll get 1 and 2, which is exactly what we need. So this one will run in n log n log n time. Let's just use this for now, and we'll think about optimizing later. So using this strategy, what are we exactly doing? Let's just do a quick rundown. All right, so step 1, get the counts of each element. And then step 2 is store elements in heap by count. And step 3, really just pop out k elements. Perfect. So yeah, that's how we'll start with this problem. Let's get into the code. All right. So first things first, like we said, let's get the counts of each of our elements. And I guess before we do that, one important thing that I think we should know is, will our input, our numbers in our array, always be positive? Because if they're always positive, we can get our counts, we can store our counts in an int array. But if they're negative also, then we need to use a hash map. So that's something that I'd clarify with the interviewer up front. In our case, let's just make a custom test case, and we'll put some negative numbers in here. And if this runs properly, then we know that this can handle some negative numbers. And if not, Leetcode will tell us, hey, you can't be using negative numbers. So I'll just return null for now, for the sake of the test. Let's run it. Oh, well, would you look at that? What is this size frequency? Oh, my bad. Because it says k is always a valid number. So yeah, now we see that with negative numbers, and we make our max number 1, we see that we're still expected to output -1. So that being said, we're gonna have to use a hash map to store our counts. Okay, so I'll call that counts hash map. Awesome. The first thing we're gonna have to do is iterate through our nums, and basically, if it's already in our hash map, let's just increment whatever value is held in our hash map by 1. And if it's not in our hash map, we're just gonna put a new key value pair with the value being 1 for that element. Okay, so we do something like for int num in nums, basically iterating. This num is iterating through all these nums. We will put the key value pair in our hash map. So we'll do counts.put num, which will be our key, and our value will be counts.getOrDefault num or 0 plus 1. So for those of you guys who don't know what this method is, it's a very cool method provided to us by the hash map, where basically if our key is already in our hash map, okay, if our key is already in our hash map, we're going to get that num, and we're going to get that key, and we're just going to increment 1. Now, if the key isn't in our hash map, let's just say we're putting in 1 for the very first time. Okay, it's not in our hash map, right? So If it's not, we're going to default to 0, and we're just going to add 1 to that 0. It's a very cool method provided to us by the hash map, very useful. And yeah, so now we have the counts for each of our elements. Now the next step is to make a priority queue, right? That's what we said we were going to do. So, and this priority queue will hold integers equals new priority queue. Now, what are we storing in the priority queue? We're storing the elements based off of our counts. So we have the elements here in our nums, and we have the counts here. So how can we put those elements in our priority queue? This is going to be another question, another type of problem where we need to change the implementation of our priority queue. And do you guys know how a priority queue normally works? Well, if we have a minHeap, okay, and we're going to put in values 3, 2, 1, it's going to hold, the minHeap will be 1, 2, and 3, assuming that the left is the top of the heap and the right is the bottom of the heap. So how is it actually like reordering these? Well, in the priority queue implementation, there is actually a comparator that's passed in. One thing that we can do is define our own comparator, just like we did in the reorder data in log files problem that we just did a few videos ago. So once again here, we're gonna have to make a custom comparator. And luckily, since we watched that video, we're like pros at that. So let's just do that up here. We'll make a custom comparator. Comparator, this one will hold integers, since we're comparing integers, and we'll call it comp equals new comparator. Oh my gosh, if I can spell. And inside of it, we're gonna need what? That's right, we're gonna need a compare method like we did before. And we're gonna compare integers in this one, okay? Integer b. Now, how can we get the counts of each of our numbers that we're going to be passing in? Well, first things first, let's, obviously this comparator, to get the counts, all we're going to have to do is do something like counts.getA. And this will get us our counts for our frequency of A. And counts.getB will get us the frequency of B. But obviously, counts is in a whole new method. Counts, the visibility of counts is between these two curly braces. So to ensure that counts can be seen everywhere in this comparator as well as this method, let's just make this global. Let's make counts a global hash map. Okay, so now this has visibility. Now counts can be visible in this method. So now, similar to the last problem, we're making a max heap in this situation, right? And I want you to visualize this. A max heap is kind of like, a heap is backed by an array. So let's just kind of visualize it like an array. In heaps, the top of the heap is the left side of the array. Okay, so top of heap will be left, and then the bottom of heap will be the right of the array, okay? So knowing this, let's just say the counts of A, and here, the way I'll do this, I'll say frequency of A equals counts.getA, and the frequency of B is counts.getB. Now, remember, there's 3 situations, and I explained this much more in depth in that last video, so if you guys, in my reorder log files video, so if you guys want to go check that one out, I think it would be very helpful for you guys to watch that video through, especially my compare method parts, my comparator parts, and then come back to this video. But a quick summary, this compare method will either return a -1, a +1, or a 0. And if it prints out a -1, that means these two, based off of the positions of these parameters, if we print out a -1, the first parameter will come before the second parameter. Okay, so that will output something like A, B. Or, in other words, in our max heap, A will come before B, and hence A will be at the top of our heap. Now, what does this mean? That means that A needs to be greater than B for it to be in our max heap, right? Now, if we print out a +1, that means according to our parameter order, since A comes before B, if we if we output a positive one, that means we're saying that B needs to come before A. Or in other words, B needs to come before A. And what does that mean? That means B is as at the top of our heap. That means the counts of B, the frequency of B, has to be greater than A. So with this information, we could basically say if our frequency of A is less than our frequency of B, that means we want B to come before A in our heap, right? We want B to be at the top of our heap. So what do we have to output? We have to output a positive number, or in this case, we'll just output a 1, positive 1. Else if frequency of A is greater than frequency of B, well, that's great. That means we want our order to be so that A is at the top of the heap and B is at the bottom of the heap. So what do we need to output to get this order where our parameters where the first parameter will come before our second parameter? We need to output a negative number. So here we'll output a negative 1. And in case either of those two don't trigger, let's just say we have two of the same numbers. Like if our input is 1 here and 1 here, well, we don't really want one to be greater than, one won't be greater than the other, one won't be less than the other. So that means we'll just return them in the order that they came to us. So we'll just return 0. That's the equivalence of returning 0. So now we have our comparator. This will be the comparator for a max heap. Okay, so let's pass in this comparator as one of the parameters of our priority queue, since the priority queue takes a comparator as a parameter. Now, perfect, we have a priority queue that will function the way we want it to function. So now, let's just iterate through our numbers and put everything in a priority queue. So here's one problem that I see us facing. If we iterate through nums, we are going to put in 1, 1, 1, 2, 2, 3. But in reality, all we want is 1, 2, and 3. Because if we were to put all of these and we were to pop out k elements, if we popped out 2 elements, then all we'll get is 1 and 1, since these are the highest frequency. But all 3 of these will be at the top of our priority queue. So is there a way where we can just get these unique elements in our counts? Well, there's another method that the hash map has, and it's called keyset. And this will give us the unique keys that are in that hash map. So let's just iterate through whatever's in our keyset. So for int key in counts.keyset, it looks like this. Oops, looks like this. Let us put those elements in our priority queue. pq.offer key. And since in our comparator we're getting the counts up here, right? It's only going to sort its elements in the order of its counts, which we've defined up here. Okay. And finally, we need what's our output? It needs to be an array. So let's just make an output array. Answer equals new int, and how many elements are going to be in it? There's going to be k elements. So let's just iterate through our answer array. I is less than length, I plus plus, and we're just going to pop off k elements from our priority queue, and we're just going to store those values in each of the indices of our answer array. So answer I equals pq.pop. Or it's not pq.pop, it's actually remove in a priority queue. And yeah, finally, we'll just return answer. And let's run that, see if that works.
They ask you how you are, you just have to say that you're fine when you're not really.
Hash map. Oh my gosh, I'm so sorry, guys. Hash map needs 2 parameters here. It needs to be 2 integers because remember, the first parameter here, or the first argument here is the key, and the second parameter here is the value. So just remember that. Sorry about that. Let's run that. Awesome. So that works. Let's submit that. Yes. All right. 9 milliseconds faster than 83. Okay, so now let's think about the runtime of this. We've already mentioned that this would be an n log n runtime. Now at this point, the interviewer will ask like, okay, is there any way we can make this even more efficient? And even Leetcode has this little hint on the side. Your algorithm's time complexity must be better than O n log n, where n is the array's size. So let's think about this. And I think the best way we can do this, let's just go back to the iPad and think about this problem. So this current solution, like we said earlier, will run in n log n time. So let's dissect how we get this n log n. N times log n. So this n log n represents the worst case time complexity. So what would be a worst case example? Well, let's say we were trying to find the top 2 most frequent elements, but let's just say everything had the same frequency. Like our input was 1, 2, 3, 4, 5. Everything has the same frequency, but we would still need to go and iterate through everything once, right? And that iteration is happening with this n. And upon each iteration, we're adding to our heap. And we know that the add operation in a heap is log of n, where n is the size of the heap. At each iteration, we are doing a log n operation. And since we're doing a log n operation n times, where n is the size of our array, input array, our overall runtime becomes n log n. But can we do better than this? Okay, well, I'm thinking at a worst case, we always need to iterate through the entire input array. So I feel like this n is important. I don't think we can do better than that. But now let's think of this n right here. Could we do better than that? Well, let's see. That n represents the size of the heap. Do we need to always keep all of n elements in the heap? I don't think so. Because in this situation, we're only looking for k elements. So what if there was a way where we could store only k elements in our heap? And this kind of makes sense, right? Because after all of our work that we're doing, at the very end, we're only popping off k elements. So why would we need to put in n elements, then pop off k right after? I think it would make more sense if we can just always store k values, k elements in our heap, and then just pop those. So what would that look like? Well, right now we're working with a max heap, right? And now in a max heap, let's just say I'll just make like a one right here, bottom. So at the top of the heap, we would have the max value by frequency. So what if we just kept k elements in our heap? Let's do a little example and see how we could possibly do that. I think it's, and here let's just say k equals 2. So I think it's safe to say that no matter what, let's always add k elements. So let's iterate through this input array. Okay, so we have 1, 2. These would be our 2 elements in our heap. And what are we storing in our heap? Remember, we're sorting our values based off of its frequency. Now, since each of these has a frequency of just 1, let's just store them in the order 1, 2. It doesn't really matter since they're the same frequency. Now, let's check 3. Does it have a frequency that's greater than the top of the heap? In this case, 1. Well, no. 3 is, there's only 1 3 in this array, so let's just keep going. 4, is there a better frequency? Is there a greater frequency of 4 than 1? No. Is there a greater frequency of 5 than 1? No. But now let's go to 6. 6, we see that there's 2 6s, so the frequency of 6 is 2. That's greater than the frequency of 1. So let's just pop off the last element in our heap. It's assuming that there's less occurrences of 2 than 1. So let's just pop off that number. And then we will put 6 at the top. We'll compare it to 1. Since there's only 1 1 and there's 2 6s, we'll put 6 at the top of the heap. Okay. So this works in this example. This would be an n log k example. Let's see if this method works for another test case. So in this particular one, we see that like our most occurring thing happened at the end of our input array. Let's try having the most occurring element in the beginning of our array. So I'm going to do some erasing here. So off the bat, we're going to store k elements in our heap. So we see that there's 3 6s and there's 1 1. So we'll put 6 at the top and 1 at the bottom, right? 1 right next to it. Now let's go check 2. Does 2 have more occurrences than the top of our heap? No, there's only 1. Does 5 have more occurrences than the top of our heap? Well, it has 2, we see, but it's not greater than 6, so we're not going to put it in there. But we notice here, just by doing like the eye check, a visual test, there's 3 6s and there's 2 5s. So 6 and 5 should be the k most frequent elements, but according to our algorithm, it's not really going to work in this case. The only way we can put 5 in is by comparing it to something that we know is smaller in the heap. Like for instance, let's just say in an alternate situation, if 1 was actually at the top of our heap and 6 was at the bottom, then we could check to see if the occurrences of 5 is greater than the occurrences of 1. And in this case, it is. So then we would just put 5 in our heap. But what did we just do there? So in this case, we had 6 at the top, 1 on the bottom. This was the max heap, right? But now if I put 1 at the top and 6 at the bottom, that's just a min heap, isn't it? So what if we just changed our max heap to a min heap and kept adding elements into our min heap only if the occurrence of that element is greater than the top of our min heap? I think that would make a little bit more sense. So let's just run through this example one last time. Or better yet, how about let's run through the example that was given to us. So on Leetcode, our original example was, and in this case, the most occurring number happens in the beginning, so we don't need to worry about anything. Now, we're going to make this not a max heap, we're going to make this a min heap. So let's store k elements off the bat. We'll store 1 and 2. Now remember, since this is a min heap, there's only 2 occurrences of 2 and 3 occurrences of 3. And according to our comparator, which now we're going to have to change, let's make sure that it's still going to be ordered based off of the total number of occurrences of each character, of each element, each number. Since there's 2 2s and 3 1s, and this is a min heap, that means 2 needs to be at the top and 1 would be right after that. Now let's look at 3. Does 3 have more occurrences than 2? No? Okay, good. So then now we just pop off these 2 values and we have an array. But now, just so we get a really big picture of what's going on, let's say we have 4 3s. Okay? So now we go to 3. We notice that there's 4 of them. Now, does 3 have more occurrences than the top of our heap? Well, yes, there's only 2 2s and there's 4 3s. So let's remove the least occurring element, which is this, number 2, and let's add 3. Now 3 would go at the bottom since there's more occurrences, and that means 1 has now the least occurrences. But once we're done iterating through everything, we are left with the k most occurring elements in our array. So hopefully that made a little bit of sense. And this is the approach we're going to do. Let's get right back into the code and let's change up a little bit of things. Okay, so first things first, let's make our priority queue a min heap. So currently it's a max heap because of our compare implementation. But to make it a min heap, it's really, really simple. All we're going to have to do is just make our current comparisons the opposite of what they currently are. So this less than, we'll make it a greater than, and this greater than, we'll make it a less than. Okay, now we have a min heap. Okay, so now let's only store k elements in our priority queue. Where are we adding to our priority queue? It's only right here. So in case the priority queue is empty, let's always make sure that there are k elements in our priority queue. And the way we can do this is if the priority queue size is less than k, let's just go ahead and add those elements to our queue. So we'll do offer key. Else, we'll have the number of elements equal k, which, we just want elements that are the number of elements to be less than k. or equal to k at all times. So if we add something, we're going to check to see if the frequency of our key is greater than the frequency of the top of our priority queue. And the best way we can do this is by doing if counts.getKey is greater than counts.getPQ.peak. Peak will give us the top of the priority queue without actually removing it. Then we're going to want to add this key. But to ensure that we'll always have only k elements in our heap, let's remove the top of our queue first. So we can do that by doing a poll. That's a method to remove the top of the heap. And then let's add our key. And this would all stay the same. So let's just run this really quickly. Uh-oh, this is the first time I've ever seen this. That is the first time that's ever happened. So luckily nothing changed. Run the code. Okay, that works. Let's submit. Make sure everything works. Perfect. Runtime is about the same, but we have changed our runtime. Before it was O of n log n, and now it is what? It's O n log k, since we always have k elements in our priority queue instead of having all n elements. So that's reducing the runtime. This would pass in an interview situation. So yeah, guys, that's how you do that problem. If you have any other problems you want to see me do, please let me know in the comments. I'll make sure to go on and do them. Let me know if there's anything I can improve on, and if there's anything you'd like to see different. And the last thing I want to do for you guys is I want to show you guys a big interviewing tip, a big interviewing key. So, this is a problem that I received a while ago, and I think I messed up on the runtime. I messed up. I also wasn't sure if I had to use a priority queue at the time, and ever since then I love, and I still do love all the priority queue problems. So, in my practice, I went and I did a bunch of PQ problems, a bunch of heap problems, and here's something that I realized. Let me show you something. On Leetcode, if you filter out the heap questions, and I'm just going to make them order by frequency just because I like doing that, notice this. Merge k sorted list, k closest points to the origin, top k frequent words, top k frequent elements, kth largest element in stream, kth smallest element sorted matrix, k and more k's, and all of these, find the kth smallest pair distance. So you guys see this little problem, this little pattern. If you see a k and a frequency in the same problem title, just know you should probably start at least with a heap. All right, that's the big tip that I will give you guys. Something that has helped me a ton in my interviewing. If I ever see anything that has a k and a frequency, I go straight to heap, or I'll think of like a worst case, a naive brute force solution, knowing that a heap is going to be used to optimize later. So this is a big tip, a big key for you guys. And yeah, hopefully you guys found a little value in this video. I'm really trying to make a few, hopefully 2 videos a week. So get ready for the next one, guys. Please let me know if you enjoyed this video, and if you guys can give me a good like and subscribe, that would be very, very helpful to the channel. And yeah, guys, hope you guys have a great rest of the day. Thank you.
Doctors of death, killing our patients to breath. We are the pain you can trust. Crooked it works.